Lecture 9.7, the magnetic field of a circular current loop. If you were to look inside many electrical or electric devices, you'd find coils with a large number of turns. So one example here is that we could talk about an electric toothbrush. Here's an electric toothbrush, and you could see that the electric toothbrush has a coil inside. So anything that's rechargeable, that's a device, will have a coil. Probably one of the most important examples here is transformers. Transformers play a very important role in society. And so when you're looking at transformers, you typically find two coils. On the left here, that's a pole transformer. And depending on where you live, you might actually see this as you go around the city here. Another super important one is the electric motor. The electric motor, I mean, I don't know how much more I could say about that. That is a super important application of a coil. But they all have coils inside. So a current in such coils are used to establish a magnetic field. And so a lot of times people will talk about, a magnetic field produced by a single loop. That's really not the useful application. When you look at these devices, you see that these devices have coils. And you could see here on your right here, that's a coil, and that's an intern coil. And over here, that's just a single loop that produces a magnetic field. So what we want to do now is that we want to calculate the magnetic field of a single loop. So we want to calculate the magnetic field of a single current loop and extend it to n turns for a coil. And the easiest coil to deal with is a circular coil because we know how to deal with that mathematically. So here we go. So I'm going to look at a single circular coil. So we're going to focus on a single circular loop. So let's look at this guy. What we want to do is we want to recreate this image right here. And I need to sort of like sketch a paper to try to get a sense of what we're looking at. So let's look at something like this. So here's our piece of paper. And so now I need to draw in a magnetic field, excuse me, a single loop. So if I'm looking at a single loop, I imagine that I'm going to start, let's say, right here. And I'm going to say that this is a circular loop. And of course, this guy is going to continue to come here. And then what we're going to see here is that this guy is going to look something like this. So now here's the so-called copper wire. So if I start to look at the direction of the field, we could imagine that we have a current coming in here and a current coming out here. So now if I start to look at the magnetic field, what am I going to see? On this side, I know that I have current coming in like this. So the magnetic field is going to wrap around here, just like it's going to wrap around over here. And you can see that I didn't draw it super well, but we could imagine that this is the middle right here. So if I was to continue to draw this, maybe I'll just extend this out a little bit more here. So when I'm looking at this, so now I could actually probably draw this a little bit further here. So now if I start to look at this guy, the one thing I need to do here is that I need to focus on the middle here where the wire, so I should see a magnetic field that should be going something like this. And this guy should be going like this. And then I'm going to start to draw my loops all the way around like that. So I'm seeing that my loops are doing this type of thing. And then if I draw one more loop in here, I'm going to say that this is what my magnetic field looks like for this configuration. Now, I could imagine that I have 2 points that I'm going to focus on for the left and the right wire. So let's say I call this guy 1 right here. I'm going to call this 2. And then over here, I'll call this 3. And then this guy right here, I'll call 0.4. Now, because of the system right here, you're seeing that I have wires that are coming in and out. And as we've already discussed, we expect that the field goes to 0 quickly if we start twisting these a whole bunch of times. So now what does the right-hand rule tell us? Well, let's look at point 1. If I look at point 1, here's my point 1. I could see that the current is going in which direction? That's the current there. And then from the wire, I have a displacement vector, which I will write as R1. And using the right-hand rule, I'm going to get a magnetic field that goes into the page, just like this is showing. So if I'm looking at it straight on, you're going to see that it's going to go into the page as we're seeing. Now, if I look at point 3 here, now that one shows that the current is still going up at that point, but now the displacement vector is now in the opposite direction. And so now I have a field that's coming out. And we could see that at point 3, that field is coming out right there. So if I do the other side, and let's say that I look at point 2 here, what am I seeing at point 2? I could see that the current has to be going down now, but my displacement vector in this situation is now in this direction, which then tells me that I have a magnetic field going into the page. And then finally, if I look at point 4, I'm going to have a displacement vector that goes to the right. My current is still going down, and therefore I'm going to get a magnetic field that looks like this. Right, so that's what I'm expecting of the field. So this is more or less a front view that we're seeing. So let me move this down a little bit, and let's say that this here is a front view. What I would say would be very important is the side view. So let's look at a side view here. So a side view has to look something like this. Now, what I would suspect is that right smack in the middle, I'm going to have a straight line for the magnetic field, and this guy is going to tell me the direction of north, and this is going to be the south direction, like that for the loop. Now I just have to fill in the pieces here. So now I could see that this guy is going to go like that. This one is going to go like this. And then these loops are then going to start to spread out. And then this loop is going to spread out. And then I start seeing these loops coming in. And I would say that that's what my magnetic field looks like from the side view. So now let's go look at trying to set up for the mathematical details here. So to calculate the magnetic field of a circular loop of radius r and current I, we have to set up a coordinate system. So my coordinate system is going to be, I'm going to pick my y direction to be here, my my x direction, and then that will be my z. So note that all of these are in the positive direction. So if I set up my loop, this is what I'm seeing. I have a circular loop. And I'm looking at these guys. And because of the way the current is running, we're going to ignore the magnetic field produced by these wires. So we only focus on the loop here. So when I'm looking at this, here's my x-axis, here's my y, and then this is going to be my radius r. But from the side view, we're going to have a loop that we only see the side of. So when I see the side of this loop, I have to pay attention to the direction of the current. So as this current is going around this loop, the current is pointing outwards here, and that's going to be IDS. The current is pointing in right here, which will be IDS, and we want to calculate the magnetic field at this point, P, which is in the Z direction. And how far is it away from the side view? It's a distance of Z from the coil. So here we go. Step one. What is the physics of the field before we calculate it? We can see from the side view that we have to have symmetry about the z-axis. We can see from the side view that there is symmetry about the z-axis. Which tells us that the field must be in the z direction. So using the right-hand rule, the little dB fields at the observation point P shows the following. So again, looking at my wire, or my loop that is, here's my loop. Now I know that I have a little piece of wire right here. And I know that at this point, the current is coming out, and I'm going to call that IDS1. So if this is my axis, the z-axis, and this is my point P here, we could pick a symmetric point right here, where the current in this case is going into, which I'll call IDS2. So if I start looking at the displacement vectors, you can see that I'm going to have a displacement vector here. Let me change the color of this so that it's not the same. And then I'm going to pick a displacement vector here. And I'm going to call this one R1, and I'm going to call that R2. So from the right-hand rule, what do I see? Well, I have a little current element right here, which is IDS1. I can see that this guy has to be in this direction. 1. So then the magnetic field has to be perpendicular to that. And if I repeat the same process as before, then this guy's going to be I ds2. Now you can see that this guy looks like this for that displacement vector. Then the magnetic field has to be perpendicular to this guy, and that's dB2. So if I put this all together, what do I actually see? Putting this all together, then I have this. I have my my single loop right here. This is my middle of the line right here. And this is my point P right here. So this guy right here puts out a magnetic field at this point that then is going to look something like this. That's going to be dB1. Now, if I look at this other piece right here, I'm going to have I ds2. It's going to put out a magnetic field that looks like this. And that's going to be dB2. So you could see that from symmetry here, I'm going to have a magnetic field that points in this direction right here. And this is going to be for the single loop, which I'm now just going to call loop. So from now on, I'm going to say that this is dB loop. And according to what this says here, now remember, this is in the z direction. So this guy should equal to 2. And I'm going to focus on just one of these. And I'm going to say that this is going to be dB1 in the z direction. That's what that magnetic field is telling me right here. That's the physics of the field. It's telling me that. So now let's go to the next piece. So now I have step 2. In step 2, we're asking how is the current element I ds1 distributed? So clearly the current is along a circular loop, and so therefore it must have an arc length that defines it. So I'm going to say that clearly the current is distributed along a circular loop. And must use the arc length to define it. So as we said before, we really, if we ignore the vertical wires here, we really have a circular current or a circular current loop. So in this situation, what are we doing? We're picking a little element right here. And we're going to say that it has a direction of current in this direction, which is IDS1. So the way we define it here is we then say that IDS1 is then going to be I, by definition of the arc length, then the only thing that changes is the direction. So this will be I R d theta. So that right there is our current element that we've just defined. So we really have a single loop, as I've already said. So now we're off to step 3. So now the dB field produced by IDS is dB of the loop, which is then going to be 2 dB 1Z. So now we want those details here. So let's start to look at that. We calculate the magnitude of dB 1Z by calculating the displacement and direction. So let's go do that. So again, I want to remind you about our coordinate system. So our coordinate system in this situation is that I'm going to have my X direction here. I'm going to have my Y direction here, and then my Z is in that direction. So if I'm looking at my coil or my single loop, I'm looking at something like this. So then I'm writing this guy as I ds1. So now let's look at this thing. So I'm going to come out here. I want to get this far enough so I can get a good picture here. So let's call this my point P. So what do I know? Where is this guy located at? IDS is located at the radius of this guy. We know that the point P, now remember, this is our origin right here, and we know that the point P is located at Z. So then if I look at my displacement vector, this is it right here. And so this guy right here is my displacement vector, and the angle has to be between R and IDS, so then this angle here is theta. So we already saw that we have a magnetic field produced by 1 that then is going off in this direction like this. So this is dB1. Now, actually, that angle is not a good representation of that angle. It should look more like this. And the reason why I do that is that this angle theta should be the same as this angle right in here. This angle is also theta right there. So when I take my vector dB1 and I break it into components, you're seeing that I'm breaking this guy, where this guy is then going to be dB1z. This guy is going to be dB1y, where this is my z-axis. So I need three things from this image. The first one that I'm going to go after is I need the z component of the magnetic field. The z component of the magnetic field is the adjacent side of the dB triangle. So in other words, dB1z has to be dB1 cosine of theta. Then I need the magnitude of the displacement. So the two other things here is I need the displacement and directional come from our triangle. So if I look at the magnitude of R, you could see that the magnitude of R has to be that this has to be big R squared plus Z squared, and the directional has to come from the cosine. So the directional of the cosine here, well, that has to be the adjacent side, because that's what we're looking at of that triangle. So then that has to be cosine of theta has to be big R, little r, which then of course is big R plus Z quantity squared divided into R. So now I have three things here. So now the thing that I have to do here is that I have to substitute all this information into the little dB loop field equation. So let's write that out. So I have dB loop. This is going to be 2 dB 1z, which is the same as 2 dB1 cosine of theta. So then I start writing out more of the details here. So then I'm going to get 2 times mu naught I over 4 pi. And then I have ds over r squared cosine of theta. And if I keep putting in these terms here, I'm then going to get this term that reads, let's see, 2 mu naught I 4 pi, and then my ds r squared term then reads r squared plus z squared r d theta times r squared z squared square root divided into r. So then finally, we could then say that dB loop is now 4 pi r squared z squared to the 3 halves. And then this will then be 2 mu naught I r squared d theta. This is a very nice integral because it only depends on integrating theta, which is super nice. So then we get to step 4. So now we need to sum all of the little dB loop terms by integrating this refreshing term. So what I'm going to do here is that I'm going to write this out in terms of arc length first, and then you'll see that I'll modify it. I will write out this solution in terms of arc length. So if I do that, I'm going to have that the magnetic field of a single loop is then going to be from 0 to theta. In our case, we know that that guy has to go to 2 pi because it's a circular loop. So I can pull everything out of the integral. So then this will be 4 pi r squared z squared to the 3 halves. And this will then be 2 mu naught I r squared, where this is then again theta of d theta. And so when I integrate the whole thing, this is what I'm going to be getting. I'm going to be getting an expression that reads 4 pi r squared z squared to the 3 halves. Then I'm going to take 2 mu naught I r, and I'm going to take one of the r's, and I'm going to write r theta here. Okay, so this, of course, is the arc length. But for what we calculated, so for a single circular loop, I'm then going to say that the magnetic field of a single loop then reads 2. By the way, there's no 2 here. Nope, I think there's a 2 there. It's going to read 2r squared plus z squared to the 3 halves of mu naught I r squared, and that is what the magnetic field is right there. You know, I made a mistake here. I just realized I made a mistake. If I'm integrating over the whole loop, then it would be 2 pi, but I'm not integrating over the whole loop. Right? We broke this down to only half a loop. So we're really only integrating over pi. So we're only integrating over pi. So that's a correction that I have to make.